Welcome back to NAND game. We are on to the Arithmetic Logic Unit, also known as the ALU. So just to get an idea of what we're doing here, the ALU is like the calculator of our processor. We put in two values, A and B, and then it outputs our results. The way this works is pretty simple. We're going to use the pieces we built already. So we're going to have things like an AND, an OR, XOR, an adder, a subtractor, and the actual components within an ALU will be different depending on the processor. Different processors have different architectures, but this is just an example. Usually we'll feed A and B into all of these, and they'll each output their own results. And each result gets put into a multiplexer, or also known as a selector. And besides the A and B values that we input, we'll also input some control bits. And those control bits will tell the multiplexer which operation we want. And the multiplexer will output whatever operation that we're choosing with those control bits. So say we define 0, 0 as our AND operation. A and B still gets fed into each one of these operations, but the multiplexer selects and then that's what will get output. Maybe 0, 1 is OR, and then the same thing happens. The multiplexer selects the OR operation as the output. So that's the conceptual overview, but now we will get in here and actually start building it. And first up is the logic unit. So we have two 1-bit flags, that's op0 and op1. Those are these ones down here, and those select which operations are performed on these two 16-bit inputs, X and Y. So 0, 0 is an AND operation, 0, 1 is OR, 1, 0 is XOR, and 1, 1 is invert. So just like in our diagram here, what I want is to add all of these components, AND, OR, XOR, and invert. And we're going to hook each one up to both X and Y, except for the invert, which just inverts X. Okay, so now we have to implement our multiplexer, but we don't have a multiplexer which can just accept this many operations at once. Instead, we have this selector, which can only accept one control bit and then the result of two operations. So we'll just have to string a few of these together. And let's actually start by looking at opcode 0 here. If it's 0, it should be X and Y. So we can hook it up to our AND. And if it's 1, it can be X or Y. Hook up to that one. But now we need to deal with XOR and invert. So we'll just grab another selector, hook it up again to opcode 0. And if op0 is 0, it can be X or Y. And if it's 1, it can be invert. Okay, I'm just rearranging it so it's maybe a little bit clearer. All right, let's just put some values in here so that we can kind of see the differences between these. So now we got to just determine which one of these two we select. And again, we can just use another selector. And we'll hook that selector up to opcode 1. And if opcode 1 is 0, it should choose the AND or the OR, which are being routed through here. And if opcode 1 is 1, it should choose either the XOR or the invert, which are both being routed through this selector. All right, so now that we can see opcode 1 is 0, opcode 0 is 1, so that should be OR. And it does look like we actually did hook these up backwards. And same thing over here. We hooked these up backwards. And this one is backwards as well. Okay, so now you can see we have opcode 1 is 1, opcode 0 is 0. We should be getting the output from XOR. So the XOR output is DF0, which is being routed through here is DF0, and then being routed through the selector is DF0. So we can try that again. Let's try 0, 0, which should be the AND output. 4 is being routed through this selector and through this selector, and then being passed to the output. All right, let's check the solution. All right, simplest possible solution. Let's move on. So now we're doing the arithmetic operations. It seems like this ALU architecture looks something like this, where we have separate individual logic components and math components. So logic component is the AND or XOR, and then math is the add, subtract, etc. They each get their own control bits. And then when we put them together, we're going to have another multiplexer to pick which output, either the logic or the math, gets sent as the final result out of the ALU. So we already built our logic component, and next is math, and that should be pretty much the same thing that we just did. So we have two opcodes and then two number inputs, X and Y. Obviously I have them as A and B here, but it's the same thing. So we're going to potentially need to deal with outputs of X plus Y, which should just be adding these two together. X minus Y, which is our subtract here. X minus Y. X plus 1. So that's just another adder. We're going to hook up the A to X here. But instead of hooking B up to Y, we're just going to hook up B to the inverter, since if the inverter is not hooked up, it's always going to be 1 being output. And then the same thing for subtract, hook the A up to X. And then since the output of inverter that's not hooked up is always 1, we just hook up the B to that. And in fact, we have an extra inverter here. We can just use this one inverter for both inputs here. And then our multiplexer setup is going to work exactly the same. So you can see it's pretty much an exact copy of what we did for the previous level. We can put some numbers in here just to check to see what happens. We have 0, 0, so that should be X plus Y output. And it does look like that is getting passed through our selectors. You can change 1. That should be X minus Y. And you can actually see that it's not working. So X minus Y should be FA2NE8, and that is not getting passed to the selector here. And in fact, if I look at the truth table here, it looks like I have the opcodes backwards. So we just got to remap these opcodes. These should get opcode 1, and this should get opcode 0. And then we can see that X minus Y is getting passed through. That's this 5828. It's all the way getting passed through the output. Let's check solution. And we've done it. Level successfully completed. Apparently it is possible to make a simpler solution, or at least one that uses fewer components. My guess would be that it has to do with the way add and subtract work, and maybe you could combine that with X plus 1 and X minus 1 somehow. I'm not going to figure that out right now, because I think this works and I think this is a good, sensible solution. Next level. All right, the ALU. The ALU combines the logic and arithmetic operations. So I figured this would be a little bit simpler, and all we'd have to do is hook up the logic and arithmetic units together into another multiplexer with another opcode, and then output the result. But it's a little more challenging than that, because we have these two flags. When the SW flag is 1, you're going to swap the X and Y inputs here. And when the ZX flag is 1, you're going to change this left operand to 0. Now, that's not too much more complicated, but it is going to be a little bit of extra work. But we can still start by hooking up the logic and arithmetic units together. So if you look over here, this U input is going to decide whether we have a logic operation or an arithmetic operation. Logic operations are 0, arithmetic operations are 1. So all we need is a selector, hook up the logic operations to 0 and the arithmetic operations to 1, and then the selector goes to this U. And then we can select the output there. Then hooking up the opcodes for the logic and arithmetic units are simple. We can just tie those directly into the inputs. So believe it or not, we have this mostly done. In fact, we could hook up X and Y to the logic unit and the arithmetic unit, and it would be mostly functional. The only thing we are missing, really, is these two control bits here, the ZX and the SW. So we just have to route our X and Y through some more multiplexers in order to get the data where we want it to go. And I think we should start with ZX, which turns the left input into 0. So we'll take this multiplexer, and for now we'll route X through it. This will have to change eventually, but we just want to see how the data flows. And then we'll hook up ZX to this switch, this selector over here, and then we're going to route the output to X in both the logic unit and the arithmetic unit. And for D1 here, we're just not going to hook up any data to it, so that when we turn it on, 0 goes into this left input labeled as X in both the arithmetic and logic units. And when ZX is 0, you still get the original input going in. We're going to delete this input for now because we will actually have to swap that around, because our SW control bit actually swaps which way X and Y are going. To see how that works a little bit easier, we'll start with Y, hook up S to SW there. And you can see in this truth table that when SW is 0, then Y should be on the right side. So we'll hook up D0 to Y. And opposite, when SW is 1, then X should be on the right side. So we'll hook up D1 to X. And then we just hook up the right input, which is labeled Y in both the logic and arithmetic unit, into this selector. And there we go. When SW is 0, you can see that this 18 value gets routed into the right side of the inputs. And if we switch it to 1, then X gets routed into the right side of the inputs. Now we just got to do the same thing for the left side of the inputs, here labeled X. But instead of hooking up directly to X, well, we already had the selector going directly into X, so we're actually going to hook it up into this selector. So this D0 is going to be the input for our selector output. We're going to hook the S to the switch. Then we can see here in the truth table that when SW is 0, then X will be on the left side. So we can hook up D0 to X, and then when it's 1, Y will be on that side. So we hook up D1 to Y. We can play with our switches and kind of check to see if things are working, but let's just check solution and see if we've hooked it all up right. And there we go. Level successfully completed, and always happy to see that this is the simplest possible solution. So as you can see, this is really about just routing all the data that we have. And that's why it ends up looking fairly complicated, even though in practice, when you break it all down, it's honestly not that bad. Okay, and this is our final level in the ALU section, condition. The 3 flags indicate 3 possible conditions for the number X. So we have LT, which means less than 0, EQ means it's equal to 0, and GT means it's greater than 0. All right, so I think this is a little bit confusing the way this is laid out, but I believe the idea is to do something like this. We have this component that's called is0, so we can funnel our X value in there. So you can see the output is 1 if it's 0, and if I change it to anything else, then the output will be 0. So we'll change it back to 0 for now, and then we have this EQ flag in the middle, which is equal to 0. So if I take an and I route is 0 and equal to 0, well, if I'm interested to know if this is equal to 0, I can turn this flag on, and if it is, the output will be 1. We're going to do the same for less than 0 and greater than 0. So we'll start with less than 0. All we have to do is add this is negative in here, hook it up like that, and then do another and. And then we're just anding it together with our less than 0 flag. What about greater than 0? Well, we have an is negative component here that checks if the number is negative, but we don't have one that's is positive. And well, there's a couple ways to go about this, but the way that makes most sense to me is just that I have this is negative, I'm checking if it's negative, and I'm checking if it's 0. Well, the only way that our number here is going to be positive is if both these values, the numbers that they're outputting, are 0. And I can check that with and. Well, not and directly, but I can invert the inputs. And now this will only be a 1 in the case that we get a positive number, because it's not 0 and it's not negative, so it must be positive. And then we'll and that together with our greater than flag. Again, I think this truth table is a little bit confusing the way it's laid out. But let's say I want to check this. I want to check if our X value is less than 0. Well, I turn on this flag. And well, the output is 0, so it's not less than 0. I want to check if it's greater than 0, so I turn on this flag. And the output's 1, so that means it is greater than 0. So you can play with this a bit to get a feel for how it works. But the general idea is that if any one of these 3 is 1, then I want to output 1. So we just want to OR everything together. So you have an OR here with 2 inputs, so we'll input these first ones. And then if we want a 3-way OR, kind of like we did with our 3-way AND earlier on, we just have to add another OR, take the output of the first OR, put that in A, and then we have a third place to put our output for the third component. Hook that up to the end, and let us check our solution. And okay, we didn't get the fewest amount of components used, we had 9. Okay, and I've just replaced the AND logic with 2 inverters into an OR inverting the output. That saves 1 component. We can check the solution, and we've used the fewest possible components makes me feel a little bit better, although I think the logic with the AND makes a little more intuitive sense. You can still apparently get this lower if you use, I guess, more clever logic with NAND gates. But I'm happy with it, and I hope the setup makes sense. And that's it for the ALU. We've completed the ALU. Next up is memory, which is not my strong suit, but we will get through it together. Thank you for watching, and I will see you in the next one.